Okay, let's consider the following problem. Suppose I have a cylindrical wire radius r through which a current I flows uniformly through it. What is the magnitude of the function radius? Be sure to draw the curve over which you apply Ampere's law. Alright, so let's draw a picture first. So my wire here, some radius r, it's an infinitely long wire, right? And what I'm going to do is I'm going to basically, there are two different kind of curves I can draw for Ampere's law. I can draw a curve in here, and I'm going to draw a curve out here. Okay, so there are two cases basically for r greater than capital R and for r less than capital R. All right. Okay, so let's basically do the two of them. All right, so let's write down Ampere's law first. It's the integral of b dot dl along some closed curve is equal to mu 0 I enclosed. All right, or through, or IC. Actually, I'm going to use IC, mu 0 IC. Okay, so this is a current that flows through basically either of these surfaces here, right? So we're going to do the first one, the easy one first. We're going to basically r greater than r. Okay, so in order to do this part, this is the easy part, this is the hard part. Okay, so let's do the easy part first. So again, basically, you have to make the argument that because of cylindrical symmetry, that B fields can be same magnitude everywhere. So this integral here, B dot dl, is going to be equal to B dl integral. So in that case, it's just this outer radii of the cylinder, r. So that's just going to be basically 2 pi times r times b. Okay. Okay, so that's basically the first thing. Okay, this is going to be equal to the hard part now, which is mu 0 times the current flowing through this. Now, in this case, for r greater than capital R, the entire current flows through. So this one's actually pretty easy. This one's just I. So then you're left with basically B is equal to mu 0 I over 2 pi R. Okay, so that's the first one. Okay, now let's do the second one, R less than capital R. All right. Okay, so again, it's the same thing on this side. Basically, B dot dl is going to be basically B, because of symmetry arguments, B integral dl, which is just B times 2 pi R. Okay, so that's the easy part. Let's set that equal to the hard part. This is going to be mu 0 times I, basically through, or IC. And this is going to be a much smaller area. So what is that going to be equal? So this is going to be equal to mu 0 times the current surface density, the current cross-sectional density, which I'll call J, times the cross-section that we have to care about, which is this piece in here. That's pi r squared. Okay, and what's J? So J is the current cross-sectional density, and J is going to be equal to I divided by the entire cross-section of the wire, which is pi r squared. Okay, so this is going to be equal to mu 0 J, what is mu 0 I over pi r squared times pi little r squared. So the pi's kill each other. Okay, and this is equal to b times 2 pi r, and so you're left with, you're now here to solve for b. So b is equal to mu 0 I r over 2 pi capital R squared. All right, and that's it for the magnitude of it.